Hi, welcome to another lecture. Today we're going to discuss what are called state vectors and introduce some of the math we need to describe our quantum mechanical systems. And we're going to use that to sort of look at the Stern-Gerlach measurements and experiments we've discussed in previous lectures. All right, we're going to start with what are called state vectors. Now, we already sort of mentioned this very briefly in previous lectures, where we mentioned that the state of our particle beam, or the state of that quantum system, was going to be described by what we call a ket, which looks something like this. Just a vertical line, some symbol that represents the ket. Typically, we use the psi as our general symbol for a general ket. And then this open or closed right angle bracket type thing. And this is basically a vector, and it contains all the sort of mathematical description of the state of that quantum system, whatever it is. This vector exists in a vector space that's called the Hilbert space. This Hilbert space can have various dimensions depending on the physics of the system you're going to describe. It can be as small as a two-dimensional Hilbert space all the way up to an infinite dimensional Hilbert space. And the state of that system is just described by some vector in that space. This is really analogous to position vectors in real space. I always like to lean on something I'm familiar with to help build my understanding. Position vectors is kind of a great way, I think, to do this with state vectors. If you recall, if you have some position of any particle in real space, you can write that position vector as a linear combination of what are called unit vectors, your I hat, j hat, and k hat. You may have written this previously as x hat, y hat, z hat. And it's basically some linear combination of those where you have a component in the I hat direction, a component in the j hat direction, a component in the z hat direction, and the position vector written as a linear combination of that. Quantum mechanical state vectors are the same sort of thing, where they can be written as a linear combination of what we call basis vectors. And it turns out this is true in math for any vector system. So you take our Hilbert space, you can define some basis vectors, and every vector in that Hilbert space can be written as a linear combination of basis vectors. So what are these basis vectors, and what do they look like? How do they work? If we think back to, again, this position vector example, what are the properties that our I hat, j hat, and k hat had? Well, the first one that they had was they were normalized. So essentially, I hat dotted with I hat was the same as j hat with j hat, k hat with k hat. They all had, they all equaled 1, right? They were unit vectors. They had a magnitude of 1. You take the dot product with themselves, and you get 1. They were also orthogonal, so geometrically this meant that they were at 90 degrees to each other. Mathematically, it meant that their inner product or their dot products resulted in 0 if they weren't on the same thing. So I dot j or j dot k or k dot I or any combination of those things, the dot product always equaled 0, right? And the last property they had was that they spanned the space, would be the way to say it, or they formed a complete set, which is, again, just what we already mentioned, that any position vector in that space could be written as a linear combination of those unit vectors, or written more compactly, it's just a sum over the coefficients times all the different unit vectors. Well, it turns out quantum mechanical basis vectors have the same properties, right? They're normalized, so if I take, if I indicate that ket as just an I hat, and I take the inner product with itself, I get 1. If I take the inner product with any of the other vectors in that basis set, they are orthogonal, so that gives me 0. And they span the vector space. So if I can write any general vector in that vector space as a sum of coefficients times the various basis vectors. Now, if we map that to the Stern-Gerlach experiments and our spin 1/2 systems that we were looking at, well, those Stern-Gerlach experiments had 2 results, a spin up and a spin down. And it turns out that those 2 vectors form a basis for the two-dimensional Hilbert space. of that Stern-Gerlach experiment, of that spin 1/2 system. So those two vectors form the basis. They have all the properties. I can write any general state vector in that two-dimensional space as a linear combination of those two basis vectors. So just some coefficient times the spin up or the plus state plus some other coefficient times the spin down or minus state. One thing that's worth noting, these coefficients A and B are actually complex. That's really important for some quantum mechanical things and has some actual repercussions later on, particularly with respect to the interference that we were talking about. And again, so because they form a basis set, they have the same sort of properties we talked about before. They are normalized, so scalar product with themselves equals 1. Scalar product with each other gives you 0. They're also orthogonal. So by now you've probably had the question of that I keep writing this sort of thing where it looks like I've kind of flipped and turned the ket backwards and written it in this form with itself and have just been pointing at it and kind of referring to it as a scalar product. What does that actually mean? What is this operation? Well, the scalar product, which is also known as the inner product or the dot product, is just an operation defined for our vector space. So if you remember, we previously defined a general ket we're going to stick to that spin 1/2 two-dimensional Hilbert space. And we defined a general ket as just A spin up plus B spin down. We can therefore, once we have that ket, we can also define a corresponding thing called a bra, which is essentially the mirror image of the ket. It looks like this, and it would be the complex conjugate of A times the bra corresponding to the spin up state, plus the complex conjugate of B times the bra corresponding to the spin down state. Right? And if we have that bra defined, we can take the inner product as just the bra and the ket, which is the bracket. Physicists are great at naming things. And we can write that operation, that inner product, this way. We just put the bra in there, the ket in there, and then we just do first inside, outside, last. We do our FOIL. We get plus and plus the spin up states, A complex conjugate of A times A, likewise the AB and that, the BB, the BA, all of these terms. And because we know how these basis kets operate on each other, we know they're normalized. So this is going to be equal to 1. This would be equal to 0. This would be equal to 0. And this would be equal to 1. This ends up just being A complex conjugate of A times A, or the modulus, essentially the modulus squared of A times B squared. You get essentially the magnitude of that generalized vector. So we can perform that inner product operation on any two vectors in our Hilbert space. So we wanted to take the inner product of, say, one of our basis bras, the spin up bra, with our generalized vector. We do the same sort of thing. We can just write the generalized vector and then bring that through, and we get A plus plus B plus minus. And since this inner product would be 1, this one would be 0, we're left with just that complex number A. This is actually referred to as the projection of this generalized vector on to this vector. And you can do the same thing with our other basis vector. We could write, just replace the spin up bra with the spin down bra, multiply it through. This would be 0, this would be 1, and we'd get B. This enables us to write our generalized state vector another way. We can write, previously we'd written it as A spin up ket plus B spin down ket. These complex numbers can go on either side of the ket. They're commutative. So bring those over to the other side and then just replace it with the projection of the generalized vector onto the basis vectors, and our generalized ket could equivalently be written this way. These sort of projections are again analogous to our projections in our familiar position vector space. So looking at, say, just a two-dimensional vector in position, we have the rx component in the I hat direction, the y component in the y hat direction. If we had our generalized vector r, and we were to take the dot product of r with rx, it would be the projection of that vector onto the I hat direction and be this vector, or the component would be this size, and likewise the y component would be this way. Now, in quantum mechanics, this projection doesn't necessarily have a mapping to a physical geometry, but you can create sort of an abstract geometry, and these inner products between one vector and another are the projections of those vectors onto each other. One final thing to know about the scalar product that's worth mentioning is that if you reverse the order of the inner product you're taking, so you get the complex conjugate. So general vector phi inner product with psi is equal to the complex conjugate of psi inner product with phi. And you can see this through a simple example that we just worked through half of it. If we take the basis spin up bra and take the inner product of that with a generalized vector, we get this, 1, 0. We just get that complex number A from our generalized vector is the projection of that generalized vector on the psi. If we do the opposite of that and take the projection of the basis vector onto our generalized vector, we get the reverse. Because the coefficients are now complex conjugates, we get a similar type answer, but now we have this A is the complex conjugate. So you can see reversing the order gives you the complex conjugate, and that's going to be something we see a lot throughout this course, so worth mentioning now. Now, the final thing that we need to discuss about these state vectors today is that in quantum mechanics, our state vectors are normalized, which is very different from the position vectors we've been kind of using as an analogy to get familiar with these things. If you recall, in position, when we were describing some position vector in real space, all the unit vectors, I hat, j hat, and k hat, those basis vectors, those were normalized. You take I dotted with I hat, and you got 1. Likewise for all the others. Whereas in quantum mechanics, all those state vectors rather, are normalized, so the inner product with themselves equals 1. Whereas the position vectors, if I have some position vector r with magnitude r naught, and these components, if I take the inner product or the dot product with itself, I just get that magnitude squared. And that can be any value. R can be at the origin, it can be away at infinity, it can be any real number. So r naught squared is going to be any positive real number for any given position vector. Whereas in quantum mechanics, if I take the inner product of my state vector with itself, I get 1. It has to be so. They are all normalized in that way. And the reason is, in quantum mechanics, these inner products relate to probabilities. And the way that works is through what the textbook refers to as postulate 4, and they apply it to the spin 1/2 system we've been discussing in chapter 1. But they say the probability of obtaining a plus or minus h bar over 2 value in a measurement of the z component of the spin angular momentum of a system in state described by this ket is just the inner product squared between the basis vector that represents that result and that generalized ket squared. So basically, if you send in some generalized vector psi, there's a particle that's described by this generalized state vector psi, and you want to know the probability that when you measure it in the spin up plus state, you just take the inner product of that plus state with that generalized ket and square it. So what that looks like is, here's my generalized vector describing my quantum system, my spin 1/2 system. I want to know the probability that my measurement will give me a spin up value. I take the inner product of the spin up basis ket with that generalized vector, and the plus inner product with the plus gives me 1, inner product with the 0 gives me 0. So all I end up with is that A squared is the probability of that spin up measurement. You do the same thing if you want to know the probability of the spin down measurement being the result, and you just change the basis ket you're looking at. Again, very similarly, we end up with B squared instead of A squared, but that tells you right away, if you recall, that our inner product of our generalized vector with itself ended up being just A squared plus B squared. This has to equal 1, right? You make a measurement, you can possibly measure it down, possibly measure it up, but if you make that measurement, you get a result, right? So you add those two probabilities together, it has to equal 1. So that's the reasoning behind why all our quantum mechanical state vectors have to be normalized, as in the inner product of a generalized vector with itself has to equal 1. Next lecture, we're going to use what we've discussed today, the state vectors and this postulate and how it relates to the measurement probabilities, and analyze the Stern-Gerlach experiments that we discussed in the previous lecture to sort of see how these results make sense in this picture and how we can use this state vector description to sort of describe the quantum mechanics involved.